but they converge, they have convergent evolution. You have the marsupial mole and the regular mole, these kind of things. Flying squirrel, and these guys, I love these things, like sugar gliders and stuff like that. Another thing that also is a pitfall of the cladistic method, again, now I'm going to emphasize how bad cladistics is, but these are very particular examples, and people focus on those without looking at, in my opinion, at the big picture that is in 90% of the cases, it works great. But in some cases, you do have pitfalls. In parallel evolution, it's a situation that is a little bit like convergent evolution, with the difference that in parallel evolution, organisms are very, very closely related, and it's the very same genes that by chance have the same mutations that result in the same outcome. We talked about the reverse transcriptase in HIV that results in this arm that prevents AZT from attaching itself. So let's say you have an organism that is in the United States, a human in the United States that has this mutation, and then you have another individual in Europe that has the very same mutation. This mutation is just by chance, however it's selected because they are taking the same drug, and so they are very closely related, and in parallel, the very same mutation happens. Now, if you were to do a cladistic tree, you would say that this organism and this one are very closely related because they have the very same mutation, while in fact, no. In two different continents, independently, the very same mutation occurred, and just by chance, and then it was selected because they are taking the same drug, but the same mutation occurred by chance, and it's in parallel. So the very same gene has the same mutation, but the same mutation did not occur in their ancestor, it occurred separately. That's why it's called parallel evolution. This is another example. This is in the case of insulin also, you have this kind of things where these green mutations are actually the very same mutations on two different branches. What is the difference between convergent and parallel evolution? When you're looking at convergent evolution, the species are distantly related. You're comparing an insect and a bird. In parallel evolution, you're taking two humans, one is in the United States, the other one is in Europe, for example. And so they are very closely related because the very same gene. The traits are usually due to different genes in convergent evolution. The genes that make a wing of a cricket and the genes that are involved in making the wing of a bird are very, very different. Instead, in parallel evolution, it's the very same gene that by chance has the same mutation. So that's, I mean, in the big picture, I suppose that it's somewhat similar, but mechanistically it's very, very different. And finally, the least common of the homoplasies, but just for sake of being exhaustive, I need to talk about it, and it's when there is evolutionary reversals. In some extremely rare cases, you have mutations that come back. And when mutations come back, then you're fooled into thinking that the mutation did not occur in the first place. In this tree here, we are showing a situation where there is an ancestral sequence at the bottom. It's a sequence of DNA. Then there is a mutation. The last nucleotide on the right mutates from a C to an A. So all the descendants have an A that is shown with the red A at the top in the 2 over there. And then you have another mutation that brings back that A into a C. That is what's called the reversal mutation. It's extremely rare, but it does happen in some weird situations. Now, if you were to use cladistics, what you would think is that the last organism does not have any difference with the very first one. And so you would artificially group them together, and you would be fooled into putting the last organism with the first one because they have similar DNA sequences, while in fact, not only it's different, but actually it went through 2 mutations. It went first through an A, and then from an A to a C. So you're counting 0 mutations, while in fact you have 2 of them. Again, this is almost esoteric because it's so rare, but it does happen.
So is that why it's important to make trees
Exactly. So this is one of the things, is that pitfalls are really bad. It's like Donald Rumsfeld that says that you are unknown unknowns. That's the same idea. Where what is really bad is when you don't know what can happen. But if you know that one of the potential pitfalls is that, then you can obviate it with, for example, taking several genes. I want to tell you though that in a situation, in this situation here, it's really difficult, and this is not far-fetched, because you're going to say, okay, we're going to use as an example, I mean, this is obvious because we look at them and we know that they're not the same, but we're going to look at the power of the jaws. Okay, all three of them have really powerful jaws. That's one character. Now let's make a tree with, you know, the muscles of the shoulders. Oh, all three of them have really strong muscles. And so now, not only you're getting to the wrong answer, but you're getting to the wrong answer feeling even better about your conclusion, while your conclusion is getting worse and worse because it's being supported more strongly, and you're more strongly arriving at the wrong conclusion. So sometimes, because characters are related, you need to be really careful. And again, this is an example that is very common, where you're starting to add more characters, and those characters are actually not fully independent. So you need just to be aware of that. But in general, the more data, the better, for sure. Okay. This lecture is a little bit complicated, but now we are towards the last part of it. So far, we have looked at the overall philosophy on how to make a phylogenetic tree. Then we have looked at what are the mechanisms, and the mechanisms is to try to find synapomorphies, to group together organisms. Okay, this is great, but what we really want is an actual outcome. What we want is to see a tree. So how do we make a tree with all this information that we have so far? So now I'm going to give you some practical examples of how trees are made. Trees, phylogenetic trees, are made with what are called phylogenetic methods or approaches, and those, there are many of them. There is a little over 50 different methods. However, thank goodness, those methods fall into three broad categories. And the three broad categories are phonetics, cladistics, and statistics. And the reason why I organize them in those terms is because that's the way it happened historically. In what computer power is every day increasing. And when we had very lousy computers, we were using only phonetics, and then later on we started using cladistics, and now people are using statistics. The last method that I will be talking about, there is no computer yet that is strong enough to actually find the solution. But it's only a matter of time before we get computers powerful enough to do it. Within each of these families of methods, I will be talking about one of them in each case. One is called the neighbor joining method, the other one is called maximum parsimony, the other one is called maximum likelihood. However, you need to know that within each one of those three major categories, there's many methods. But they are all pretty much the same. So I'm going to start with phonetics because it's the easiest one, then cladistics and statistics. Any questions so far? Good. Phonetics. Phonetic methods are what are called distance methods. And distance methods have a number of advantages. First of all, intuitively, they are really easy to understand. Meaning, you know, usually people always ask me, oh, can you tell me if this one is more distantly related than this one? Just by saying distantly related, you're already in the realm of phonetics. You're talking about distances. And another thing that is really satisfying about phonetics, phonetic methods, is that it's easy to do, and the result is always a single tree. And finding a single tree is really great because the last thing we want is to think too much. And so you have a tree, you're done. The reason why the computing is easy is because here you have 4 species, 4 organisms, and I showed some DNA sequences. But it could be morphological characters, it could be behavioral characters, it could be anything. And the first thing that you're going to do is that you're going to tally the differences, which are shown here with the little asterisks, and you're going to make a matrix, which is the one on the right. So the one on the right is computing how many differences are present between all the different 4 species. Now, the reason why the method is easy to do for a computer is that the original data set is the one on the left, but the data set that is used to make the tree is the one on the right. And regardless of the size of the original data set, the matrix is always, in this case, 4 by 4. So the matrix is very, very small because it's just a single number for each pair of species. So here, instead of having, whatever, 15 nucleotides, if I had a full genome, it would take me a long time to tally the differences, but eventually the matrix would just be a 4 by 4 matrix. The number would be large, it doesn't really matter, a number is a number, but the matrix is very small. And so that's why computationally it's really easy to do. And in fact, you can do it by hand very easily, which is what I'm going to do next. So it's a really easy method so it's called neighbor joining method. I didn't write it down, but that's what it is. So you have this matrix here. First, you're going to start with the smallest of numbers. In this case, is number 1. There is a single mutation, is this one here. And you're going to start from that, and you're going to find what is the neighbor of that. This is why it's called neighbor joining. You're going to start with a small number, and you're going to find the neighbor of that. So this is what we have. We have the matrix, and then we're going to join the smallest of the number. There is an ancestor. The ancestor is here, and the distance between A and B is 1. So this means that from the ancestor to here, you had 0.5, and between here and here is 0.5. So to go from A to B, it takes 1. That's the unit. That's how I came up with the 0.5. And then you're going to say, okay, now we have this, the very beginning of the tree. Let's try to find what is next. And so to try to find what is next, you're going to average the distance between A and everything else, and B and everything else, and whatever the average is the smallest will be the next organism. So in this case, you do, what is the distance between A and B compared to C? The answer is 4.5. And what is the distance between A, B, and D? And the answer is 7.5. 4.5 is smaller than 7.5, and so C is going to be the next organism. You see the way it's done is that the distance between A and C is 4, the distance between B and C is 5, the average between 4 and 5 is 4.5. That's how I found this. And the distance between A and B of D is 7 and 8. The average between 7 and 8 is 7.5. That's how we come up with 4.5 and 7.5. And then because you need to go down and then back up, 4.5 divided by 2 is 2.25. That's why here there is 2.25. And then, I don't know, but 0.5 and 1.75 is 2.25 as well. So as you can see, this tree is really easy to make, just back at the envelope kind of stuff. And if I had a full genome, the numbers would be larger, but they could still be doing it even without a calculator. And then you just find the last one. The last one is the distance, the average distance between A, B, and C, and the rest. And so that's the average of those 3 numbers. And then you find where D is. And then you just keep going. That's why it's called the neighbor joining. You just keep going, and eventually you have a full tree. So it's really easy to do. It works, it's great. That's how trees are made. If you use the phonetic method, which is a distance method, it uses a distance matrix. Really easy, it takes a fraction of a second when you have a computer, even with a small calculator or any laptop. It's really very, very fast. Are there any questions about this method? Very good. Now, we are going to talk about the cladistic method. And the cladistic method uses characters instead of distances. So the way you're going to do it is that you are going to draw a tree between A, B, C, and D, and you're going to look at the characters of A, B, C, and D. In a case of a DNA sequence, you look at the very first character, the very first column. I don't know if it works, but yeah, this doesn't work, but that would be a column here. So this would be AAAC, for example. In this case here, I drew GGAA. That would be the first column. And so the idea, when you look at this, is that you say, well, the most likely scenario, the most likely thing that happened in the history of these organisms is that the ancestor of A and B probably had a G as well, and the ancestor of C and D probably had an A. And now, just for the sake of argument, I just put a G as the root of that tree. It could be something else. Just bear with me, I just put a G in there. So now, how many mutations are necessary to make this tree? Well, the answer is just one. Because if the ancestor has a G, then if you have a single mutation in the entire tree, then the G turns into an A, and then the descendants have an A. The synapomorphy for C and D is an A, it's a clade, and the value of this tree is what is called one step. One step means one mutation. Now, what you need to determine, however, is this the most likely outcome? Well, now you need to test the other possibilities. The other possibilities is that actually the arrangement of the tree is not ABCD, but it's ACBD or ADBC. Sorry about that. There's crickets in my cup. I would answer her, but she just looked at these. So, so this is what happens, is that in this situation, to explain the whole scenario, it requires 3 mutations, and in the other one, 3 mutations as well. So in one case, you have what is called one step. In the other cases, you have what are called 3 steps. Now, it's called maximum parsimony. Maximum parsimony means that what we consider the more likely outcome is the outcome that has the smallest number of steps. So the smallest number of steps is the top one, so our preferred tree would be the top one. Now, this is for a single column of the data set. Now we need to move on to the second column, and the third one, and the fourth one, and for each column, you need to make these assessments. And at the end of going through the entire sequences, you need to tally how many steps were in each of the 3 scenarios, and see which of the 3 scenarios has the smallest number of steps. So for the first column, as it turns out, the top tree is the preferred one, but you could imagine that after 100 columns, maybe this one would be preferred of the other one. And so, as you can imagine, for a computer, it's not very difficult, but it just takes quite a bit of time to look at all the different topologies. These 3 are called 3 topologies, and then assess how many steps are for each column. So it just takes a lot of time. It also presumes there's an assumption that is very strong, which you may or may not agree with, and the assumption is that evolution proceeds with the shortest possible pathway, which in itself is problematic, because it's not always the case. Just to give you an idea, these were unrooted trees, so with 4 taxa, you actually have 3 trees. That's the 3 we looked at over there. Now, if you had only 10 species, you would have to assess more than 2 million trees. So now you have 2 million topologies, and for each topology, you need to address every single column. So very quickly, 10 is not many, only 10 species. You have to look through millions and millions of iterations to determine which of the trees is the shortest. And as you may imagine, in some cases, many of them, you have many trees that have exactly the same number of steps. This means that there is not a single answer to your question, what is the correct tree? And so, because of that, the phonetic method is a lot easier, and it doesn't require much thinking. There is one tree at the end, and then you're done. Instead, this one requires a huge computation time, and at the end, you end up with 10 trees that have the same score, and you say, well, this is cool, but now what am I going to do with 10 trees? It's still very nice, but go ahead.
When would you actually use the phonetic method?
When do we do the phonetic method?
As an example of when would you use it?
The method that I'm going to talk about later, next, is going to be maximum likelihood. Each method has advantages and disadvantages, but to be fair, in 99% of the cases, all 3 methods produce exactly the same tree. And so, because of what I just said, the phonetic method is the go-to method because it takes less than a second for pretty much anything. And then you have a tree, and you say, okay, now I have a pretty good idea of what to find. Now, the reason why you use other methods is because of the pitfalls that I talked about earlier. Each method has pitfalls, but they are different. And so when you use the 3 methods, then you say, okay, if the 3 methods give the same tree, then you say, I feel pretty comfortable saying that this is the correct answer. If the 3 methods end up with different outcomes, then you say, well, why is it? And so then you can figure out if you have homoplasies, if you have problems with what are called molecular clocks, you can have a lot of different problems. And so the answer to your question is you always use the phonetics, but it's not the method that you rely on exclusively. But because the 3 methods almost always give the same outcome, it's kind of a really easy method to use. That's why I use it all the time, just to say, okay, I just got results, I want to very quick and dirty. What is the answer? Okay, this is the answer, I feel very strongly about it. Now that I know what it is, let's spend another 3 weeks running the computers and seeing if I find the same results or not. Just to give you an idea of what I was talking about number of steps, and to go back to the example of the evolution of the eyes, vertebrates and cephalopods have those eyes that are very similar. Now, you can say that the eyes evolved by convergent evolution separately. This is the tree that is found using other methods, and where there is the orange bar, it's where the eye evolved, and so the eye evolved 2 separate times. But another way of saying it is, well, actually, no, I don't believe this. What I think is, in fact, the eye evolved only once, and then some organisms lost the ability of seeing, they lost that organ. And so if you do that, you say, okay, the origin of the eye is actually at the base of the tree, of the ancestor of both cephalopods and vertebrates, and if you put it there, you need to add a number of losses. And this tree, just if you count the number of bars, has more steps than the previous one. This one has 2 steps, this one instead has whatever many, 5 or 6. And so by maximum parsimony, you would say, well, my guess is that actually the the other tree is more likely because it requires less mutations. So that's an example, a very practical example of how these things work. There is a difference between phonetic and cladistics in what is the overall approach. In distance trees, you want as many characters as possible because you want just to establish the best possible distance. In cladograms, when you use cladistics, when you use cladistic methods, you are only counting the synapomorphies. Only the synapomorphies are going to group together organisms. That's the only ones that matter. The monophyletic status, which means that's what is determined by synapomorphies, is the requirement of a clade. It's not a requirement for distance trees, it doesn't matter. And the emphasis is the branch length in one method, and the other one is you want to split the branches to be able to group together monophyletic assemblages. And the outgroup in a distance tree is not required, and in a cladistic method you want to root a tree. That's what we talked about earlier. So that's the sort of philosophical differences between the two approaches. Okay, last but not least, a method that is extremely intensive for computers. It's somewhat satisfying. I have misgivings about it. I mean, I like all three methods quite a bit, but there are a bunch of issues with statistics. But what is interesting about it, especially now when people are using more and more genetic and genomic data, is that so far we have not talked about something that is absolutely fundamental, that is, how do you come about having organisms that are different in the first place? And the way this happens is because of mutations. Mutations have occurred, and then we are all looking different. And so if the fundamental basis of evolution is mutations, how come we don't talk about them when we are making trees? Well, we don't because it's complicated. But if we could, should we? The answer is yes, we should. And so statistical methods are methods that are actually taking into account what is really happening at the very fundamental parts of a phylogenetic tree. And so a method that uses that is maximum likelihood. So I'm going to go a little bit in some details, but bear with me a little bit. So there are 4 nucleotides in DNA, A, T, G, and C. Those nucleotides can change from one to the other, and that's what a mutation is. We have an entire lecture on mutations, but a mutation is when a nucleotide turns into a different one. And when you change from one nucleotide to another, you have a certain likelihood, a certain proportion, a certain chance of having a mutation. So there is a number of models. There is 60 or 70 models of mutations. I'm going to only talk about the 2 main ones. One is what is called the Jukes-Cantor model, and is that the chance of changing from one nucleotide to another is a probability that is called alpha. And so what you're going to do is that you're going to model the chance for a nucleotide to turn into something else. In this case, you have the probability for A in a specific position to turn into a different nucleotide. And that probability is 3 alpha. Because the probability for A to turn into a G is alpha, probability for A to turn into a T is alpha, and A and C is alpha. Actually, every single probability is considered alpha, is the same. So probability of changing is alpha. So the chance for an A in a specific position to change is 3 alpha, and I don't know if it's not shown here, but the chance for A not to change is 1 minus PAN, which is 1 minus 3 alpha, there's no change. So when you're going to make a tree, you are going to look at every single nucleotide in every single position, in every single organism, and compute how likely it is for that organism to have its sequence change from whatever it has to anything else. So every single nucleotide of that organism needs to be assessed for its likelihood to change. And this is for every single nucleotide, for every single individual. As you can imagine, this is extremely complicated. Not only is it complicated, but this is in the simplest model, which actually doesn't occur in real life. The second simplest model is what is called the Kimura two-parameter model. Otto Kimura was a discoverer of the theory of neutral evolution. We will talk about that at some point. But what he considers, correctly so, is that nucleotides are not identical. There are purines and pyrimidines. Purines can mutate into another purine. Pyrimidines can change from one to another. Pyrimidines are C's and T's. Purines are A's and G's. Some have one single ring, the other one has two rings. And so because of their space and the hydrogen bonds that they make with the other strands, they mutate differently at a frequency that is different if they are a purine or a pyrimidine. So the chance for A to turn into a G into an A, or a C into a T and a T into a C is alpha. And this is to turn from a purine into a purine, or a pyrimidine to a pyrimidine. These are the two top ones. The top one and the very bottom one. These are very, very likely to occur. These are called transitions. Transitions. Transitions turns purines into purines and pyrimidines into pyrimidines. This is A turns into G, G into A, or C into T, or T into C. So the probability is alpha. If you are changing from a purine into a pyrimidine, or the reverse, which are the crosses or the ones that are vertical, then it's called a transversion. Transversions. The frequency is different. In general, this frequency is 10 times less than this one. In general, that's sort of back of the envelope kind of calculation of people that have looked at how likely is it to happen. That gives you an idea of how often mutations happen. I have an entire lecture on mutations, and I'll develop that a lot more. But right now, just imagine the transversion. Transitions and transversions are the kind of words that you want to remember for the rest of your life. These are actually really important concepts. Mutations are not the same. You have transitions and you have transversions. This is really fundamental understanding of how life works. So these ones, purines turn into purines, pyrimidines into pyrimidines. Transversions instead, it's a purine that turns into a pyrimidine or the opposite. So they are the vertical ones or the cross ones. So because you have that, the chance for A to change is alpha. Alpha is A turns into a G, plus 2 beta, that is when A turns into a T or a C, that would be a transversion. So alpha is a transition, and 2 beta would be a transversion. Yeah, go ahead.
And typically with this second model, are we to assume that beta is usually going to be a larger number? Like it's harder to change between purine and pyrimidine than purine and pyrimidine?
That's right. So one of the cool things that Kimura, it didn't escape Kimura's mind, he said, the cool thing about my model is that if you really like the Jukes and Cantor, you can make beta equals alpha, and then it turns into Jukes and Cantor. But you can make it into anything. The other models, you see that here you have whatever, maybe 4, 6, you have 6 numbers over there. There is 2 alphas and 4 betas. There are a lot of models that actually have different values for each one of those arrows. And then models also change if you go from a T to an A to a T. And the reason for it is because actually all those mutations are not equal. In real life, each change is really slightly different. So you have very different models. But the bottom line is, to be able to get to a tree, you should take the sequence of all the organisms and then estimate how likely each organism is is likely to change into a different one, and try to estimate the likelihood of that. This method is really cool, and no one has ever been able to apply it. You cannot do it. So everybody agrees that this is how it should be done, but there's no computer that is powerful enough to do it. And so why am I talking about it if we can't do it? First of all, because it's super cool, and then that's how it should be done, and at some point it will happen. And another thing is that we actually get to it differently. So in one situation, you have 4 organisms, you have their DNA sequences, and you're going to try to calculate the likelihood for each nucleotide to change, and you're going to try to estimate a likelihood on how these guys are organized with each other. We cannot do that. So that would be the ultimate goal. Instead, what people do is they do something that is different. They have a tree that is A, B, C, D, and then they have another tree that is the other tree that I did, so it's A, C, B, D, and then A, C, B, D, and then the other one. And they are not asking with this data set to come up with the correct tree. Instead, they're saying, these are the potential trees, and what is the likelihood for this tree to be correct? And so here we are generating a tree. Here we are saying this is the correct tree. What is the statistical value for this tree to be correct? And so you are giving an outcome and asking to the computer to calculate what the overall likelihood of this tree is. So now, if there is only 3 of them, it's really easy enough. But when you have thousands of them, it becomes really complicated. So, because when you have thousands of them, it becomes really complicated, you can't do it. And so what you do is that you are going to, when you have, let's say, 25 species, you are going to give the computer a random tree. Whatever tree it is, it doesn't matter. You're going to give the computer a random tree, and you say, what is the likelihood of this tree? And it's going to come up with a number. And the way it calculates it is that it sees what the relationships are, something like this. And it says, okay, to go from here to here, you need to have that many mutations, and that many mutations you can calculate with these formulas what the likelihood is. And so once you have that tree, the tree is going to be the tree is going to be this number 1. And it's going to be in a landscape that you don't know, in a landscape of probabilities. And then what you're going to do is that you're going to change a single branch. You're going to change one branch, and you say, what is the likelihood of this new tree? And there's going to be 2 outcomes. Either the tree is not as good, and you're going to reject it, or the tree is going to get better, and you're going to accept it. And little by little, you're actually starting in a random place, and then little by little you're going to go up until you reach the top, and that is the correct tree. And then when you're at the top, every single change is going to get worse, because every time you go at a statistical value that is lower, and when it goes back and forth a certain number of times, you say, okay, stop, we are at the correct tree. And so this system is not finding the correct tree from scratch. Instead, it's finding the tree by small iterations. And so the method actually kind of works. And so the problem is that this is what the landscape looks like. And in some cases, you can be in places like this, and you go up and you're not in the correct tree. So you need to redo it many, many times to know that many times you end up in these places here, and then you go to the correct top, and there are other subtleties that I don't need to go into details right now. But so the maximum likelihood method, it cannot be used to obtain a tree directly from scratch, but you can reach the correct tree by small iterations, by slightly modifying the tree every time. So there are three main methods. There is phonetics, that is super simple. You just make an assumption of distances. You can do it by hand, and you end up with a single tree. You have cladistics, where you're going to try to find synapomorphies. You're going to assess the different types of trees, and then you're going to determine which one is the shortest one. And the last one is statistics, where you cannot really make the tree de novo, but you can slowly trend towards the correct tree. And importantly, all three methods, when the data are very robust and very clear, always find the same tree. So it's really almost academic. The more interesting cases, of course, is when the situations are very difficult. But when the situations are not very difficult, then you obtain the same. I want to talk about a few more things just to wrap it up. Phylogenetic trees are hypotheses. They are not set in stone. Right now we have data and we feel comfortable with the results, but these are things that need to be revised all the time. So right now the data show this, but in 2 years if we get more data, things may change. They are really hypotheses. It's really important to keep that in mind. And because most of the time people use some genes, we are looking at gene trees, not species trees. Because some genes may be under selection and they may be prone to convergent evolution, give you a lot of confidence into the wrong topologies, but the reality of it is that what ultimately you're interested in for taxonomic reason or for anything else, for evolutionary reason, is that you want species trees. Species trees depict the evolutionary history of a group of species, while a gene tree depicts the evolutionary history of a specific locus, of a specific gene. And so most of the time they match, many, many times they don't. So you need to be really careful about that. A good example of that is the relationship between humans, gorillas, and chimps, where people have, for the longest time, had a hard time determining which are the closest relatives. Our closest relatives are chimps. There are two species of chimps, and after that you have gorillas. The outgroup is the orangs. But the reality of it is that this is true when you do the entire genome, but there are tens and tens of genes that are closer between humans and gorillas than they are between humans and chimps, because those genes are in the selection, or because the chimps derive very much, or because we derive a lot. And so this is a good example of a situation where there's a big difference between gene trees and species trees. That's it. Thank you guys very much. We see you guys on the